it is time to proceed with the construction of the root locus. Actually, when I explained to you in the previous examples in the MATLAB, I already have shown to you the things that we need to consider in order to construct the root locus. So in this case, what we want is actually we want to plot the root locus by hand without using the software. All right. So now we have the characteristic equation of the closed loop transfer function. We have delta S equals to 1 plus kgh equals to 0. As I said before, the root locus begins at poles and ends at zeros. And as you can see from the examples of camera and motor system, the value of k is 0 at poles, and the value of k become infinity at zeros. Okay? These poles and zeros include those at plus minus infinity. But for the scope of our linear control system, we only consider where we have the value of k at infinity. Okay? Alright. Say this example we have here 1, 2, 3, 4. We have 4 poles, meaning that we need to have 4 endings. We have 4 beginnings at poles. We have 4 endings, which one at zeros and another 3 at infinity. Okay, we have these 2 poles comes together to the breakaway point. One goes upwards, one goes downwards to the k equals to infinity. And to the k equals to infinity. And this poles at -2 ends at -3. Okay, and we have the last poles here at -4 ends at infinity. Okay, properties number 2. Number of branches of the root loci is equals to the order of the polynomial. Okay, from the characteristic equations, we know that the maximum polynomial we have is power of 3. We can just actually refer to the number of poles, from the loop transfer function. Okay, we get the number of branches is equals to 3. Properties number 3. Note that the complex conjugate poles and zeros, if any, are always located symmetrically about the real axis. Thus, we can say that the root locus is symmetrical about the real axis. So, in the next example, we can see the poles or zeros that is located on the it's a complex number. It's a complex number, which means that it is located on the S-plane, where we have both real and imaginary component. Okay, so we can say that if we have this complex number is a complex conjugate. So basically, the root locus is symmetrical about the real axis. So let's say if we have -3 plus j3, we also have another poles at -3 minus j3. So it is symmetrical about the real axis. Number 4, the angles of asymptotes of the root locus as s approaching infinity. Okay, so the RL, the root locus, are asymptotic to the asymptotes with angles given by this theta k equals to 2k plus 1 multiplied by pi, or 180 degree, over n minus m, where n is the number of poles, m is the number of zeros. Okay, so k is actually the number of asymptotes. K is the number of asymptotes. So K equals to n minus m. N minus m. Okay. And we have properties number 5. We have the intersection of asymptotes of root loci lies on the real axis at S, which is we can find the sigma 1 by using this formula, the summation of poles of KGH minus summation of zeros of KGH over n minus m. Okay? So, in this example here, we have this a system with a unity feedback where we have zeros as plus 3 and we have poles at 0, -1, -2 and -4. Alright, so number of poles is 4, number of 0 is 1. So the number of asymptotes is 4 minus 1 equals to 3. So we need to have, in order for us to draw the root locus, we need to draw the asymptotes. The asymptotes is 3, 4 minus 1. So we have 1, we have 2, we have 3. Okay? So how do we know the intersection of asymptotes here? We can use the formula here, the summation of poles minus summation of zeros over n minus m. So we have poles at -1, -2, -3. Actually, we have a 0 here. And then we minus with zeros, which is minus -3 over number of poles minus number of 0, 4 minus 1. What we get is -4.3. So this is the intersection of asymptotes. So this is the intersection of asymptotes. And we can calculate the angle of asymptotes using the formula given 2k plus 1 multiplied by pi or multiplied by 180 degree over absolute value of 4 minus 1. K is the number of asymptotes. So we have 3. So we have k equals to 0, k equals to 1, k equals to 2. So we put k equals to 0 in this formula. What we get is pi over 3. We put k equals to 1 in this formula, we get pi. And we put k equals to 2 in this formula, we get 5 pi over 3. Okay, this is the angles respectively. Alright, so when you plot on the MATLAB, it does not give you the asymptotes. It does not give you any asymptotes on this root locus. However, if you use Scilab, we have Scilab. This is an open source software, and I have uploaded the codes for these examples in the Google Classroom, so you can try. So what I do is I just run this first example here. I run, so right click, I evaluate selection, and then what we get is we get this plot here. Okay, so this is the root locus drawn by using Scilab. The extra features of this Scilab is we can see the asymptotes. So in this example, we have 1, 2, 3, 4, 5. We have 5 poles and we have 1 zeros. So the number of asymptotes is 5 minus 1 equals to 4. That's why we have 1, 2, 3, 4. And we can find the intersection of these asymptotes here given by the summation of poles minus summation of zeros over n minus m. which in this case I think it's about 2 something. Okay, and we can find the angle of asymptotes using the formula 2k plus 1 multiplied by pi over n minus m, and then we get the angles here. I think the angles is about 60 or 45, around this one, these angles, and these angles, and then we can draw the asymptotes. So what is the importance of these asymptotes? Okay, this actually, when we draw the root locus, these root locus must not cross the asymptote. So the asymptote is like a boundary of the root locus. So you can see here, the root locus goes from here and then goes upwards, and it travels along the asymptotes, but never cross the asymptotes. Similar to this root locus, when it has the root locus between these two poles and goes to the breakaway point, one goes upward and one goes downwards, and then it travels along the asymptotes and never ever cross these asymptotes. Okay, next. Number 6, properties number 6, RL will be in the section of real axis if the total number of poles and zeros of KGH to the right of the section is odd. This is actually what I simplified to you just now. When we have poles and zeros on the S plane, on the real axis, what we can do is we just connect the first point, whether it is pole of zeros, to its adjacent poles or zeros. So in this case, it's poles. So we connect the first poles to its left, and then we don't have any root locus, and then we have another root locus between this 0, -3, and -4. It is alternate. We have root locus, we don't have root locus, we have root locus over here. Okay, so in this example here, we have many poles and we have 2 zeros. So we have this RL root locus between this first pole to the left, and then we don't have any root locus. We have root locus between this 0 and pole, and then we don't have any root locus, and then we have root locus between this 0 to the left. Okay, so in this example here, we have actually this location, either it is complex conjugate, or it wants to say that we have 2 poles on the same location, which is in this case is S square, which is S at 0 and S at 0. We have 2 poles at 0 here, so basically we connect these 2 poles at 0 and at 0, and then we don't have any poles over here. We don't have any root locus over here, and then we do have root locus between this pole and 0. We don't have any root locus, and then we have root locus between these 2 poles over here. Alright, next. Properties number 7. The angles of departure or the angles of arrival of a root locus at a pole or 0 respectively of KGH equals to the angle of tangent to the locus near the point. So this is the formula. This is the summation of angle of 0 minus summation of angle of poles. Okay. Okay, this is the angle of departure. So when we say an angle of departure, it is actually when it departs from the breakaway point, ataupun it departs from the poles. Departure is actually always from the poles, right? Always from the poles. So the angle of especially we have these complex number, we have complex poles, it departs from these locations. It departs from these locations. So this is the angle of departure. And when we say the angles of arrivals, the angle of arrivals is the angle at which it goes to the zeros. So this is the angles of arrival. Okay. Alright, let's see this example here. We have k s plus 2 over s plus 3 s square plus 2s plus 2. So for a point S1, okay, for a point S1 near root locus at pole negative 1 minus j here, negative 1 minus j. So we can find the angles. We know that from the characteristics of the root locus, the summation of angles at one point, S1 in this case, is equals to 180 degrees. So we take the angles of theta 1, theta 2, theta 3, and theta 4. So the angles of all these poles and zeros equals to 180 degree. Yeah? Or we can say that multiply of 2k plus 1 of 180 degree. So in this case, it is calculated that when we have this, we want to find angle of departure at theta 1 here. We can find the angle at S1 near 1 negative 1 minus j is equals to theta 1 equals to 108 and 4 degree. Okay, so this is the angle of departure. Okay, we will revisit this example in the next example in details. Okay, so properties number 8, intersection of the root locus with imaginary axis, if any, can be determined using Routh-Hurwitz criterion or property number 10. So you have learned the Routh-Hurwitz criterion when we have a system that intersect to the let's see, to the right, to the j omega axis. Okay, we can find it using the Routh-Hurwitz criterion, and we can find the frequency of oscillation at this position. Okay, at this position. So whenever the poles on the j omega axis. Okay. All right. And we can use also property number 10. What is property number 10? Let's see after this. So we have property 9. We have 9.1. So breakaway point of the root locus must satisfy dk over ds equals to 0. Why we want to find the differentiation of dk over ds? So basically when you see the mathematical problem, so when we have this shape, for example, we have this maximum and minimum curve. So dk over ds is finding the minimum or maximum of this transfer function. So we take dk over ds to find this position, this minimum point. That's why we get this. We use this formula to find the breakaway point. And when we find the breakaway points, we might find a few breakaway or a few numbers of breakaway points given, especially if it is a higher order of polynomials. But the complex conjugate solutions are breakaway points. Okay, these breakaway points is actually valid if it lies on the root locus. Okay, all real solutions are breakpoints for root locus. And we might find the complex conjugate, but the complex conjugate solutions are breakaway points only if the points are on the root locus. Again, we will revisit these properties in the examples. Let's say for this, we have this characteristic equation here, 1 plus kgh equals to 0. So we have here, when we find the k over ds, we can find s at these two position, negative 0.4 and negative 1.5. Okay, let's try to plot this. Let's say we have here k over s plus 1, s plus 2. Okay. Okay, we have our g1 equals to transfer function of we have 1 because we don't have any 0 here, and k we always assume when we plot it k equals to 1, and we have poly of poles 0, negative 1, negative 2. So 0, negative 1, negative 2, and we can plot our locus of G1 here. Okay, and we can find okay, so we can find actually the breakaway point is valid at this point, negative 0.4. So we have negative 0.4 here. This is valid. And we have another one at negative 1.5. Negative 1.5 is actually located here. So this is not a valid breakaway point because it is not on the root locus. Alright. This is another example of how to find the breakaway points. So I need you to go back and look at these slides to understand how to find the breakaway point. Another method to use is, we call it transition method. So this method requires no differentiation, but what we can do is we take we have this kgh here. So our kgh is equal to k over s plus 1, s plus 2. And what we do is we use this formula here, the summation of 1 over zeros equals to the summation of 1 over poles. So in this case, we don't have any zeros, so it is 0 equals to 1 over s plus 1, 1 over s plus 2. And then solve this equation. What we get is we get s equals to negative 0.4 and s negative 1.5. This is the same examples in the previous 9.1 properties, so you can check. And this is another example, so I need you to go to this slide and then do on your own, so that you can get the idea of how to find these breakaway point using two methods, which is dk over ds, and another one is using transition method. Okay, and finally the properties number 10. So this property says the absolute value of k at any point s1 on the root locus is determined from the equation k equals to 1 over absolute gh equals to 1 over m equals to the pole length, product of pole length over product of zero length. So actually we have done this example in the previous slides. Okay, so I need to go back and revisit the slides where we have these examples here. This is slide 25. So we have finished 10 properties of how to construct the root locus. We will do the construction of the root locus in the next lecture. So okay. So see you in the next lecture. If you have any comments, please just ask me in the lecture or in the WhatsApp. All right.